We were talking about shortest paths, dynamic programming for the problem of finding the shortest path from each node V to some node T. And we developed an algorithm that was order n cubed time, worst case number of operations. And if you remember the structure of that algorithm, why it was n cubed, is because it had an outer loop which was for each k equal 1 to n. So this was specifying that your path lengths, okay, I know I'm using a different notation than last time. I think that was I. Anyway, the path length could have I edges in it, okay? And so we were enumerating path lengths, and actually this goes up to n minus 1. And then what did we have? We had for each V, for each vertex, okay? And then we had, you're going to compute opt of, I think the notation was VI, using the recurrence relation for opt. Is that the correct notation? People have notes? Oh, reversed? Okay. But at any rate, so this in here, this recurrence relation, we said was, its time bound was bounded by order n, because what did it do? It looked at all the possible first places that you would go from V. So it was something like you were going to minimize over W every possible vertex, and you're going to go from V to W with that cost, which might be infinite. If there's no actual edge from V to W, that was infinity. And then you were going to opt from W in I minus 1 edges. And we also had the possibility of going from V to T and with I minus 1 edges. Okay, so this is the same recurrence. It's probably not written exactly the same as last time, but it's the same logic. And the point is that this was order n because you were looking over all vertices, all possible vertices. But many of those vertices weren't actually neighbors of V. Generally, if you look at a graph, even if it looks very, very sparse, no, if it looks very dense, okay, but you actually figure out how many edges there are compared to how many there could be. And there could be n choose 2, roughly n squared divided by 2. If you actually calculate how many edges there are, it's usually a very small percentage of what there could be. So this is something sometimes I do on airplanes when I'm bored. You pull out the map in the back of the magazine that's there, and it just looks like spaghetti. You know, just especially if it's an airline that goes a lot of places. You know, you've got all these lines, but you actually calculate, count how many edges there are, and you'll see, and then how many nodes there are. You see, it's a very, very small fraction of what there could be. Okay, and by the way, when you're looking at this big spaghetti mess, you don't count one edge at a time and mark each one, because you'll just get lost with it, hopelessly lost in that. Instead, what you do, of course, this also can get difficult too when the picture is too dense. But so I could, if I want to count the number of edges that are in here, I could say, okay, that's an edge, mark it off, that's an edge, mark it off, and so on. But when there are just tons of them, and especially when they're long, you're looking at this big map, and it's just lots and lots of edges around there. You look at one and you make a mark over there, and then you're looking over here, and you have to trace it and see if you've already marked it. It's really, you just get totally lost that way. So instead what you do is you look at each node, and you count the number of edges that touch it. Okay? And that's the degree of this node. If this is V, NV is the degree of that node. Okay? And then you sum them up. You sum up these counts. Okay, so summation, the degree at V, you sum those counts up. Now, this is easier to keep track of because you're right there and you're looking at all the ones that are incident there. Of course, sometimes these pictures are just, right there it's full, so you have to come out a ways to see the individual edges. But the point is, what's the relationship of this sum to the number of edges? It's what? Well, okay, the way I asked the question, what's the relationship of this to the number of edges? Is what? Proportional. Okay, proportional, that's true. Anybody else see it? Yeah.
Twice the number of edges?
Yeah, it's exactly twice the number of edges. Twice the number of edges. Okay? And that's because every edge gets counted twice. This edge, for example, gets counted at one endpoint and gets counted at the other endpoint. So every edge gets counted twice. So when you make this sum, you divide by 2, and you have the total number of edges. And by looking at the nodes instead of the edges, you can keep your sanity and hope to actually get the proper count. But even if you're off a little bit in the airplane, it doesn't really matter. The point is still that you end up with what looks like a total spaghetti mess. And it turns out, I don't know, it's 0.5%, or that's not 50%, it's 0.5% of the potential edges are actually there. It's very, very sparse, very small. So getting back to this question here we're counting order n to evaluate this recurrence for a fixed I and a fixed V. But I was just saying that generally the total number of edges that are coming out of a node is much less than n. N is the potential that there could be, okay, or n minus 1. For a node, it could have an edge to every other node, n minus 1. But generally, in realistic graphs, that's not true. So if instead of writing this, look at all W that are nodes, what instead we're going to do is just look at W, where V to W is an edge. And as I was saying last time, you have to organize the representation of the graph in adjacency lists, not an adjacency matrix, because if it's an adjacency matrix, then or an array, when you're at node V, you'd be looking along a row for V to see what are these values, or equivalently, is there even an edge from V to W? And then you'd still have the order n time. But if you have an adjacency list, then when you're at node V, you just look down that list, and all you're encountering are the nodes W, where V to W really is an edge. So let's do the analysis now of what the running time is when we use this speed up. Okay? Well, we still have this is for each I from 1 to n minus 1, so that's going to go around n times. And then for each V, okay, we're summing over the evaluation of this recurrence for that V. The I is fixed when we get into here. So we have to sum over the evaluation of these recurrences for all the V's. Okay? But for each V, you're going down its adjacency list, and the number of nodes you're encountering is what? In terms of the notation that's up on the blackboard, when you run down the adjacency list for a node V, you're encountering all of the neighbors of V, all the nodes for which there's an edge from, say, V to W. And what is that in terms of the notation that's up here? Well, I said this is NV. This is the degree of V. It's the number of edges. Well, I said here this is the number of edges that touch V. Okay, so I guess the answer to my question is that it wasn't, the notation wasn't actually up here, because this notation is for an undirected graph, and now I'm talking about a directed graph. But it's related, okay? So let's make up some notation. So NV with a hat on it, with an arrow on it, this is going to be the number of edges directed out of V, or from V, okay? And so when you fixed an I, that's in this loop, when you fixed a V, the amount of work to evaluate the recurrence for I and V is proportional to this NV with an arrow on it, right? Because you're just walking down the adjacency list for V, looking at all the nodes that such that there's an edge from V to that node. So the total is that. The total work in, so now we're saying for a particular I and a particular V, it's NV with a hat. Okay? So this work, what's the total amount of work for this portion in here? So every time you go in here, what's the total amount you have to do? You have to look at each V, and then for each fixed I and fixed V, you have order NV with this arrow. So every time you enter into here, how much work is that? It's up on the board right here, right? It's the summation over all the vertices of the number of edges that are directed out of V. Okay? So this is summation NV, that's over all vertices. And what is this sum equal? Is what? Well, before we were counting every edge twice because it was an undirected graph, and we were counting an edge from one endpoint and from another endpoint. Now we're counting each edge only once because we're only counting it from one of its two ends. The edge is directed, and we're only counting it from, if it's like this, we're counting it from this end. Now, I don't know whether that's called a head or a tail. I've only been dealing with graph theory for over 40 years, and I still can't get that terminology down right, whether this is called the head or the tail of a directed edge. Somebody find that out and let me know. Okay, but at any rate, you're counting from this end, the head or the tail. And so this is exactly the number of edges. Okay? So what's the total running time of the algorithm when you have this modification now? You've got the outer loop that goes n times. You have the inner loop that whose running time is order E. So the total time is order n E. In the book, E, this size of E is denoted as m. Well, that's order nm. Okay? So instead of n cubed, it's order nm. And m, generally, what I was saying, m is generally much less than n squared. N squared is roughly, you can divide that by 2. That's the potential number of edges, or roughly potential number of edges. Although if it's directed, you could even have something like that. Okay? But the number that you actually have is generally very small in comparison. So this is an improvement over, now I'm misusing notation, but anyway, I just mean to say that this is an improvement over that in most cases. Of course, m could be as big as n squared if we had every possible edge, in which case these two are the same. So it's beneficial to have the small data structures issue a change in their implementation to have an algorithm that really runs faster. Okay, so I did that very, very quickly last time, and I just wanted to do it more thoroughly today. Now, I had planned actually to that this was going to be the last topic in dynamic programming, but it's somewhat unsatisfying to leave it like this for the following reason. In Dijkstra, Dijkstra's algorithm computes the shortest path from some single source to every other node. Shortest path from S to each V. Now, I don't remember how the book presented it, whether they really emphasized the fact that you're getting the shortest path to every other node. It might have been just in terms of the shortest path from 2 specified nodes. But the same algorithm in the same worst-case running time actually gets the shortest path from your start node S to each node V in the whole set of nodes. And you do that in what time bound? Pop quiz. What's the time bound for Dijkstra's algorithm? Closed book pop quiz. Okay. Who's gonna get the extra point here? What's the time bound for Dijkstra's algorithm? Yeah.
Is it n log n?
N log n? No. Yeah. N squared is what we usually say. Actually, the n log n is not right, but there is an implementation that might have been closer to n log n than. But anyway, n squared is the n squared time. So suppose we have the following problem in a graph with no negative weight edges. We want the shortest path distance anyway between each pair of nodes. Okay? So if we have this problem, now you're given an undirected graph, or it could be, Dijkstra would work for directed, but at any rate, you're given a graph, and there are no negative weight edges. And now, instead of finding what's the shortest path from a single designated source to everybody, you want to know what's the shortest path for every pair of nodes. You just want to know what that number is for every pair of nodes. given what you know so far, what's the fastest algorithm you would suggest? What's the best way you know to approach that problem? Yeah.
You use the original Dijkstra for all n nodes.
Yeah, you could just run Dijkstra's algorithm n times, varying what the source is. Actually, if you think about it, if it's undirected, you only have to do it n minus 1 times. But at any rate, if it's directed, you can do it n times. But either way, you see that if you just run Dijkstra's algorithm n times, that's sufficient to answer this question. And so in the case that there are no negative weight edges, that implies order n cubed time is sufficient. Okay? So in n cubed time, you can find the shortest path between every pair of nodes, as long as there's no negative weight edges in the graph. All right, now let's look at the similar problem. If there are negative weights, well, anyway, there are no negative weight cycles. If there are negative weight edges, but no negative weight cycles, directed cycles, then given what you know how to do, what's the best you would suggest for solving the all pairs? You want shortest path distance between all pairs of nodes, then what's the best that you can suggest for that problem? Somebody has to have an answer. I don't see anybody. I don't see any hands up. I don't see any hands. Yes, I see your lips move. Oh, well. What's the answer? No, that was you. Allison.
I'm confused as to what the shortest path is.
Sorry, what?
I'm trying to figure out, what is the shortest path distance?
Distance?
What are you asking? What is the shortest path distance?
Oh, okay. Okay. That's not grammatically well stated. What is the shortest path distance for each pair of nodes? So it's the same problem as what was over here. It's just that now we're in the case of we have negative weight edges, but no negative weight cycles. Okay, so here we wanted the shortest distance between each pair of nodes. So for every pair of nodes, it should find what's the distance. And if we run Dijkstra n different times, varying the source each time, you would learn that. Okay, I'm asking really the same question. It's just on the case of when there are negative weight edges but no negative weight cycles. So you want the shortest path distance for each pair of nodes. Okay. All right, so what's the answer?
Using that algorithm.
Yeah, we can use this algorithm. Did we ever give this a name? I don't know we did. But anyway, you can use this dynamic program for, and you would do it how many times? Just n times. Again, this is the shortest path, to, it's from each node V to some node T. Now maybe the 2 adds an additional layer of complication in thinking about it, but if I vary now the sink, or the terminal node, and I compute for that particular sink what's the shortest path from everybody else to it, and I do that over all possible terminal nodes, Then if you specify, okay, I want to know what's the shortest path from I to J, well, you look up when J was the terminal node, and what was the value you computed from I to J. So you definitely have that information. So here, this was, in the case of Dijkstra, it was the shortest path from. In the case of this dynamic programming algorithm, it's the shortest path to. But if you do this computation here for each possible terminal vertex, terminal node, then definitely you'll be able to answer this question. So here we run the DP, the dynamic programming, n times, varying the terminal node through all possible terminal node. The grammar here is terrible. Making each node the terminal once, and that will solve this problem. And what's the running time of that? Is what? I saw your lips move. Can't escape. It's what? N squared E. Well, okay, if we're going to take, if we take NE as our running time for a single terminal, and we're going to do it n times, then it's N squared E. Okay, that's, and what if we don't use the sparse version? If we don't use the sparse, this is called the sparse bound, because it's exploiting the fact that m might be much less than n squared. So the graph might be quite sparse. And this is called the dense bound. What if we use the dense bound? It's what?
N to the fourth.
N to the fourth, right. Yeah, so N to the fourth. And that's the way the book leaves it, essentially. That for the case of no negative weight edges, you can solve this problem in n cubed time. But for the case of negative weight edges with no negative cycles, it would take you n to the fourth time. So it looks like there's a big difference between these two cases. Yeah.
Does that seem varying the terminals?
This one?
No. Run the DP n times, and then I'm not sure what that works.
Varying, yeah. Or I could just n times, making each node the terminal once. Let's just take this out and it'll still work. Okay? So it looks like this problem is harder than this problem because this has an n cubed time bound and that's an n to the fourth time bound. But in fact, there's a classic algorithm for exactly this problem whose running time is not n to the fourth, but n cubed. And so I said a few minutes ago that it's kind of unsatisfying leaving this topic where the book leaves it, because it leaves you with this kind of uneven impression about these two different problems. So I want to talk about the algorithm that solves this problem in order n cubed time. But order n cubed is possible. And that's called the Floyd-Warshall algorithm. And I don't think it's in the book. I didn't find it in the table in the index. But there's a perfectly good explanation of this on Wikipedia. Okay, actually, someday I'm going to try to teach this course just from Wikipedia, because it's got plenty of stuff in there, and you can save yourself $100. Of course, it doesn't have homework questions, but at any rate. So if you just look up on Floyd-Warshall or Wikipedia, most of what it says is fine, with one exception, which I'll get to at the end. So it's also a dynamic programming. Which means there's a recursive way of looking at this problem, and then there's a way of organizing that recursive computation. So instead of being top-down and very expensive, you can organize the computation bottom-up and very efficiently, in fact, in cubed time. So let me just introduce the notation. This is a definition of the notation. SP IJK finds the shortest path distance, denotes, not finds, denotes the shortest path distance from node I to node J only using nodes from the set, I'm running out of space, from the set 1 through K. All right. So in this notation, the nodes are all numbered by integers 1 through n. Okay? So previously we were using V to represent a node and so on, but now the nodes are labeled with integers 1 through n. So I can talk about the set of nodes 1 through k. All right, k is less than or equal to n. And I should have put the word intermediate. Right there, intermediate nodes from the set 1 through k. Now let me just give a little picture of what this kind of looks like. So shortest path from, let's say, node 3 to node 7 using nodes only from 1 through 5. So we have a graph, got lots of nodes. Here's 1, here's 2, 3, 4, 5, 6, 7, 8, 9, and so on. And what this notation means is that you want to find the shortest path from node 3 to node 7. So somehow it's going to go in the graph from 3 to 7. But the only nodes it's permitted to use as intermediaries, the only nodes that path can use, other than the two endpoints, the intermediate nodes must come from the set 1 through 5. Nodes 1 through 5. So you can't use node 9, you can't use 8, you can't use 10, and so on. The only nodes you're permitted to use are from 1 to 5. Now, you don't have to use them all. It may be that there may even be a very short direct edge, but it may be advantageous to use some intermediate node, and as long as that comes from the set 1 through 5, that's legal. Okay? So that's our recursive notation. Now we have to find recurrences to express that. So what is SPIJ 0? Well, what is it? What is the set 1 through 0? That's the empty set. Okay. So this is saying, what's the shortest path distance from node I to node j using no intermediate nodes? Well, it's one possibility is infinity. That's if there is no I to j edge. Okay? Otherwise, what? It's the weight of that edge, and let's grab some notation. Cij, if I to j edge exists. Okay, so this is the base case. The shortest path from I to j that does not use any intermediate nodes is just either infinite, or it's the weight of the direct edge from I to j. Okay. Then we have to think recursively. In the general case, shortest path from I to j using nodes 1 through k as intermediaries. So you don't have to use them all, but you can't use anything other than the ones from 1 to j, 1 to k. All right? So, as in the development of most recurrences, you have some cases. You have to think of what are the meaningful cases here, and they have to be in terms of some parameter set here that's smaller. It's a sub-case, sub-problem. What variable here seems like you should vary it to find a sub-problem? You've got 3 parameters there. Which one do you think you should vary to get a sub-problem? Yeah. K, yes. So I and j are sort of what you're trying to connect. What you're trying to connect, that's your target. But k is what's giving the constraint. And by varying k, you get sub-problems with different constraints. So one possibility, if you're going from I to j, one possibility is that the shortest path to get there that is permitted to use 1 through k, it's permitted to use nodes 1 through k, but it turns out it's not advantageous to use k. It could be that the shortest path from I to j that is permitted to use nodes from 1 through k doesn't use k because it's just not advantageous. So what's the shortest path in that case? What's the notation for that possibility? Okay. Yeah. So this is just SP ij k minus 1. The shortest path from I to j, where the only intermediaries you use are from 1 through k minus 1. That's one possibility. Okay? But the other possibility is that you do use k. You want the shortest path from I to j that only uses intermediate nodes from 1 through k. That's all it's permitted to use. And in fact, it actually does use k. So what does that look like? Well, it goes from I, and it goes to k, and then from k, it goes to j, right? Now, what are the nodes that it uses in here? That is between I and, what are the intermediate nodes that it uses in here? What set does that come from? From 1 through k minus 1. Why just k minus 1? K is already used, no. So we're saying this is the shortest path from I to j that uses nodes just from the set 1 through k. And here's where it's using k. It actually is using k, and it's right here. So between this I and this k, the intermediate nodes I'm claiming do not involve k. Because if they did, suppose you went through k here, all right? So from here it's k, and then you're coming back to k. That's a cycle. This graph has no negative weight cycles, so at best, that weight of that cycle is 0. Otherwise, it's even positive. So there's no need to ever go through k in this segment, in this section. You get just as good a shortest path from I to j using nodes from 1 to k if you say, in this segment, we're not even going to use k. It's going to be forbidden. So what is the shortest path? What's the length of the shortest path from I to k under those conditions? You're going from I to k, and the only intermediate nodes you're permitted are from 1 to k minus 1. So in terms of our notation, what's the length of this path? Oh, okay, hands, yeah.
Is it SP I, J, K minus 1?
Yeah, so this is going to be SP ij k minus 1. All right? What? Oh, I to k, yes, right. Sorry, absolutely. Okay, that's that. Now what about from k to j? Is k in here? No, for the same reason. If k was in here, then there would be a cycle, and that cycle would be pointless. So what's the distance from, what's the notation for the shortest path from k to j that only uses nodes from the set 1 through k minus 1? I know you wanted to answer the last time.
Okay, SP k to j, j minus.
And what do you put here?
J minus 1.
What?
J minus 1.
J minus 1? K minus 1. Right, you're only off by 1. J and k are the same in the next two. Okay. And of course, you have to add those together. So that's the recurrence here. And then you take the best of those two possibilities. That's min. Okay. So this is, yeah.
Why couldn't that second part just be the length of the edge from k to j? Like, why are there intermediates between k and j?
Why what?
Why are there intermediate nodes between k and j?
Why are there?
Yeah.
Well, it could be. I mean, you take a graph where, New York and San Francisco, well, of course, there could be a direct flight, but, or wherever, whatever you're modeling. But it could certainly be advantageous to go through some intermediate nodes. Or you just take two nodes that don't have a...
You being the nodes from I to k, because those are from 1 to k minus 1.
Yeah.
So wouldn't you be going back to k minus 2 a second time? Would that be a cycle? What if k minus 2 was between I to k, and then it could also be between k and j, right?
But then it can't be.
Okay, so you're asking what... All right, so we argued that you couldn't have k in here. All right, that's true, but you could have k minus 2. All right, and you're worried that you're going to have k minus 2 in here. Okay, so, all right, that's a good question. In fact, I drew that picture. It's right there. Yeah, that's a really excellent question. That case has to be looked at to convince yourself that these are right. So here's the shortest path from 1 through k, and then the shortest path from k maybe goes back like that. And although this is not k, this could be k minus 2, something like that. Yeah. All right. But, yeah, this is really an excellent question. Because, does anybody see what the answer is? Yeah.
Because it wouldn't, the optimal path wouldn't go through k. It would only go to k. It would go to k minus 2, and then it would go straight down to k.
Right. You could go like this. Okay. And this path is shorter or equal to this path, because this is a cycle, and we have no negative weight cycles, and this path doesn't use k, and therefore this length is up here. Okay? So yes, you're absolutely right. These two things added together could give you two paths that look like that. But if that happens, then this value, this distance, is going to be greater than or equal to what this distance is. And then when you take the min, this is going to be the winner, or they'll be tied. But yeah, absolutely right. So yeah, so we need to take a look at that to convince ourselves that these recurrences are correct. Okay, but assuming these recurrences are correct, and they are, and we have the base case. Now, what's the running time of this? Okay. Well, I didn't show you how we're going to organize the computation. What's the natural way to organize this computation? What's the outer loop going to be? We only have three possibilities, ij or k. What's the outer loop? Well, in the recurrences, you're really varying k. And for that value of k, you're looking at all I and j. So the outer loop is going to vary k, and then the two inner loops will vary I and j. Okay? So that's the way you can evaluate these recurrences. Okay, now if you don't know what goes inside here, that makes a homework question. So you could organize the dynamic programming this way, and that implies what running time? N cubed. Because k is varying from 1 to n, and I and j are there are n different nodes in here. And so you're getting a big O of n cubed. And in the end, this, of course, gives you what the shortest path is, because SP ij n, that's the length of the shortest path from I to j, under no constraints at all, because you're permitted to use every node as your intermediate node. So when you get up to n, SPIJN is the shortest path distance from I to j. And in this computation, you've computed that for every pair ij, and so now you know what the shortest path distance is for every I and j. Now, there are two issues left. One is the traceback, because you might actually, it's after 3? Oh, shocking. Okay, we're done. I had to leave early.